Okay. Today we have with us Professor Ted Adelson. He's a professor of vision science with us at MIT, both in the Department of Cognitive Science as well as CSAIL. He's also a member of the National Academy of Sciences, a life fellow of the IEEE, and the recipient of the Nakayama Medal in Vision Science. For much of his career, he has worked on human vision and computer vision on topics such as multiscale image representation, motion perception, material perception, and plenoptic imaging. In recent years, he has been working on artificial tactile sensing. Most of you will have probably heard of GelSight, an optically based touch system that exploits the high resolution capabilities of cameras for touch sensing. I'm excited to see how these enhanced tactile capabilities enable effective robotic manipulation. Welcome to the seminar.
All right, thank you. For this audience, I'd like to give a little of the backstory, background on how I got interested in touch sensing. And it begins with my girls when they were little. I was fascinated with the way they used their fingers. And here's an example of my daughter, Robin, picking up these necklaces. And I was just very impressed with the way she did this. She picks them up, she puts them over her head, and this is especially interesting. I was intrigued by this kind of action here where she grabs two strands with one hand and then she lifts it up and she lets go of one strand but holds onto the other strand at just the right moment so she can get it over her head. And she does that action repeatedly. So she's got an amazing combination of touch sensing and motor control. And so I was just very impressed by this. And I asked Leslie what she thought was going on here, or what roboticists knew about how one could replicate this kind of performance. And Leslie said, well, we really don't know much because we don't have fingers like that. You would need to have soft, sensitive fingers in order to perform this sort of stuff. We don't have it. So I asked her to show me what she had, what she was working on, and she showed me this Barrett arm, which cost $150,000, including the hand. And I said, wow, that's really expensive. Why is it so expensive? She explained it's extremely precise, and it's extremely precise because robots need to, if you think of robots as moving things around, moving themselves and things around in the world, you need to know exactly where everything is in order to get the robots to do what they need to do. That means the robots have to go exactly where you say that they're supposed to go. And that is how much of robotics was at that time, because this is 15 years ago. So sensing was pretty bad. Both tactile sensing and vision sensing were not as easy to do as they are today. So people didn't rely on them. So you relied on this kind of precision. But I thought, Robin is not precise. So how could Robin do what she does? And here's Robin grabbing a train, and that looks simple enough, but consider what she's doing. She's got this really floppy body. Her movements are very complicated. She can't possibly have a really good plan on exactly what she's going to do at every moment. So how does she do it? How does she get there at the right place at the right time? Well, she's using feedback, right? Throughout this part, even though she's flopping all around and moving, her eyes are just laser focused on that train, and she's using her eyes to help her keep adjusting the movement she's doing so she can get her hand at exactly the right place. And then the tactile sensing is going to take over and tell her hand, okay, now it's time to grasp it. So if you're going to work with sloppy hardware, you have to have feedback. That's key. And if you want feedback, you have to have good sensors. So sensors are really critical in enabling robots to do things. Okay, now I want to digress and just explain a little more about where I was at that time. I had problems with my feet. Podiatrists were unable to figure out what to do, so I started building my own orthotics in my apartment. And by the way, that meant I had a bandsaw in my kitchen, and that meant that when Ruth was pregnant with the kids and her mother came and visited, her mother said, "You can't have a bandsaw in the kitchen if you have a baby." So I got rid of the bandsaw. But I was mixing up, making molds and working with silicone rubber in order to put these things on in my shoes. And I also happened to have metal flake pigments because I was working on problems in the perception of materials. I was interested in reflective properties of surfaces, so I was making different surfaces. And those things came together at this moment when I was thinking about touch sensing and say, well, I could do this. I could make a touch sensor this way. Take a chunk of clear elastomer, put some metal flake pigments on it, and then look at it with the camera. And you can see everything that's happening. You can see all the distortions of the surface. And we call that GelSight. And then I had a postdoc in my lab, Kimo Johnson, who was a vision guy, like everybody was in my lab at that time. He figured out how to do some nice photometric stereo on it, so you could go from these images to 3D models of the surface. And from there, I hooked up with Mandayam Srinivasan, who was in MECI. He's retired now, but Srini is really a pioneer in touch and haptics, both human and machine. And so he taught me everything I needed to know to get started. And we wrote a little NSF grant together. Rayleigh, Wenjun, Yuan, and Xian Dong built some sensors. We started making progress. Here's Siwan's sensor holding a potato chip. And you can see the corrugations on the screen. And then I wrote a bunch of NSF proposals, and they were all rejected. And they were not just rejected, they were rejected. You know, they weren't even near to being accepted. They were really roundly rejected, to the point where I finally was feeling very discouraged and thinking, okay, never mind, I'll go back to vision. Then John Leonard said, hey, Danielle is setting up this big new program with Toyota, and they're going to be sponsoring stuff with cars and stuff with robotics. Why don't you send something to them? So I did. TRI liked it. And that turned out to be incredibly important because it meant I could work on this, and it's then really enabled me to do everything I've done in the last number of years. So thank you to TRI. And as time goes on, as I'm learning more about robotics, I'm learning more about tactile sensing, and I see some themes emerging on what tactile sensing is good for. And I'll talk about some of those things in today's talk. So one is providing feedback, as I was just discussing. You can't have feedback without sensing, and tactile feedback is one of the important kinds of feedback. And another thing is providing geometrical information. Now that's what we get naturally out of GelSight. It's a sensor of geometry. And we thought, like many people think when we began, that force was the important thing for tactile sensing. But I've come to believe geometry is really the important thing. And I'll talk more about that. And then you can use tactile sensing to estimate the properties of the objects in the world that you're picking up. all the shape of the objects, their physical, mechanical properties. These are all important things that tactile sensing can do for you. And let me start with discussing something that people are puzzled about, because many times people are afraid of the idea of having a soft finger and a soft sensor, because they figure everything's going to be imprecise if you've got this fuzzy, squishy sensing manipulation device. So, and that can be true. So on the left is an imaginary capacitive sensor covered with some rubber. And so the capacitors don't get the touch signal until it's gone through that rubber. So they're fuzzy, the signals are fuzzy. Likewise, for that resistive elastomer in the middle, the same story. It's going to be a fuzzy information. But with a camera-based sensor, that's not true. The camera's looking at the skin, and it's giving you precise information because cameras, that's what cameras do. They tell you about the geometry of what they're looking at. They naturally do the 2D geometry, that's what the image is telling you. And then with machine vision, you can get the 3D geometry. And so it can be perfectly precise if you're doing something camera-based. And there really is still this feeling in the robotics community, in many people, that force is what tactile sensing is about. So for example, here's a chapter where the title is Force and Tactile Sensing. And force is important, of course, but I think it's mostly not what's important in tactile sensing. Tactile sensing is about spatial patterns, which is geometry. And here's some examples. Suppose I pick up a pen. I'm holding it. So what am I feeling? Well, I'm feeling force, indeed, against my finger. I am applying force, so there is some force information. But there's all kinds of other stuff. I'm sensing the shape of the object, how it sits in my finger, the fact that it's a cylinder, the fact that it's round, the fact that it's positioned with a certain pose, the fact that with this pen, I'm holding onto the rubber piece, so that's a little bit soft. I can feel that. I can also feel the texture of the place I'm holding it. I can feel whether it starts to move. I can feel whether it starts to slip. And all of these, including force, can be estimated from the geometric information I'm feeling at my fingers, with the deformation of the skin of my fingers. Another important thing is that I'm using the word force here, although I really should be using displacement since I'm talking about geometry. But anyway, touch involves both normal force and tangential force. And everybody thinks about normal force, that is the stuff that's pushing against your skin. And almost all touch sensors are designed to pick that information up. It's more difficult to measure tangential force or tangential displacement, the stuff that goes along the skin. But that information is really important because that's the information that tells you about friction. And friction is really important, right? If you're doing manipulation, friction is really important. Friction is all tangential. And it happens that GelSight can, if we put some dots on the membrane we're looking at, it can tell you about tangential forces and displacements just as easily as it can tell you about the forces and displacements. So it turns out it was just, it's really been lucky that GelSight, which was just started out as an idea about how to visualize touch information, really provides you very rich and very useful information. So here's an example of a geometric measurement, slip. Right, slip what is slip? It's the relative motion of the object and the finger. So obviously that's an important geometry-based measurement. Let me talk about another measurement, which is hardness, something you feel immediately when you pick an object up. If you pick up a tomato, you want to know if it's ripe. If it's hard, you know it's not ripe. If it's soft, you know it is ripe. That seems like it's a force-based measurement, right? Because you feel like what you do is you squeeze with your fingers and you see how far it deforms based on how much force you apply. Because that's the way hardness is defined in, it's basically a kind of a spring constant. How much displacement do you get from how much force? But humans can measure hardness of a tomato, for example, without doing that. You can stick your finger passively on the table, face up, and close your eyes, and somebody can press a tomato on your finger, and you can tell how hard it is. It's you just have to try it, and it's just immediately obvious to you. Right now, you're probably thinking it's not. There's no way you could do that. Turns out you just do. And you immediately know how. You don't have to think about it. It just feels soft. And what's going on is your finger has some level of softness. The tomato has some level of softness. When they push against each other, they each deform. And whichever one is softer deforms more. So if it's a hard object, it doesn't deform, and your finger deforms. If it's a soft object, it doesn't deform as much. It deforms a lot, and your finger doesn't deform as much. Anyway, and we can see that in some videos. Here is a tomato being pressed against the GelSight sensor. And this is a soft tomato, and over here is a hard tomato. And you see the hard tomato really forces the sensor to deform a lot. Let me go back to the soft tomato. The soft tomato only does a little bit of deformation of the sensor. The hard tomato does some serious deformation of the sensor. And you don't need to know force. If you have that sequence of images showing how the deformation changes over the sequence, you can calculate hardness. So with purely geometric information, you can get hardness. And Wenjian decided to build a hardness estimator for general shapes. For a single shape, it would be easy, but if you want to do it for more complicated shapes, it's more complicated. And so she pressed GelSight sensor against lots and lots of shapes. She had to make all these shapes because we needed a database to train on. So she actually physically made all these shapes, different softnesses. And then, to make a long story short, she was able to use that to estimate the hardness of, by the way, hardness is just a generic term that people use to mean hardness and softness. Anyway, it worked. So let's see, and here she is just demonstrating it on an avocado. So she takes two avocados. As a human, she can feel, oh yeah, that one's harder, that one's softer. And then she can go with the GelSight sensor and get a number. This is on the Shore 00 scale, or double up scale, as they call it. Here's another number. Now, we don't have ground truth on these avocados, but we can say that the ordering of the avocado softness is the same as the human ordering of the avocado softness. Anyway, so basically, that does what we needed to do. And it's based on the geometry that we get out of our tactile sensor. Now, the next important phase of my work in GelSight was when I started collaborating with Alberto Rodriguez and his group. most of you probably know, Alberto is a world expert in manipulation and more recently, and increasingly, an expert in tactile sensing too. And so this has been a tremendously important collaboration for the direction we've gone. Working with his group, we developed a more compact version of GelSight called GelSlim. And we also started working on real-time reactive control, which I will tell you about next. In other words, seriously trying to use feedback to get as close as we can to real-time manipulation of an interesting thing. And so that's encapsulated in this paper on cable manipulation. And here's the human task. You slide your fingers along this cable in order to find the plug, and then you plug the plug in. Something we do very simply. What we are doing without thinking about it is, first of all, we're modulating the force that we're using to squeeze on the cable so that it can slide, so we don't squeeze it too hard or too soft. And then we're also adjusting the way we're moving so as to keep the cable in the right place, and then to adjust the pose of the plug when we plug it in. All right, so we built a special gripper for this, because if you're going to use feedback, you need to be able to move fast. Your sensor has to be providing the data pretty fast, and your gripper has to be able to react fast, because otherwise it's the whole thing's excruciatingly slow. And so let's see this gripper. It's doing grip here. We're getting data out of it. The data is telling us about the position and the sliding of the cable between the fingers. And so we first have this problem. We have to grip just right, not too hard, not too soft. I'll skip over the details here. There's a controller to estimate that and keep track of it and adjust to get things right. Then pose control. We've got to keep track of the position and orientation of the cable between the fingers, and we've got to move the arm in order to adjust for any dangerous signs that it's going to slip from out between our fingers. And here is the gripper on the arm doing that. It's moving around in order to keep it between the fingers. And it's doing that well, as demonstrated by somebody trying to make life difficult for it by disturbing it, but it's adjusting in order to keep it in between the fingers. And then there's this other task, which is insertion. And because it's picking the thing up at a kind of random position, so it has to calculate the pose and then adjust for the pose so that it can get it in. So it has to move the arm and also has to change the angle. And so here they are combined, and there it is, it works. So we would like this to be real time. It's not quite real time. There's a 4x speed up. You can see in the corner. But that's pretty good, and we're pleased to be able to get something like that working. Oops, this is getting away from me here. Okay, so we think this is a really cool framework for doing things like cable manipulation, where we've got multiple controllers going, well, in this case, 2 controllers going at the same time, keeping track of different things, both using tactile sensing. And it allows us to do something that's never been possible before, which is to do cable manipulation in free space and almost in real time. All right, now let me tell you about another recent piece of work. This is which we call Swingbot. And here's the task. That's slow motion. That's that's swinging this thing up. So think of this like a pen. If I give you a pen and ask you to hold it between your fingers and swing your arm to get the pen up like this, you can do that. You practice a few times, you can get pretty good at it. But now I say, okay, close your eyes. I'm going to give you a new pen, which has different weight, different friction, different properties. And I want you to do this on the first try. And you won't be able to do it on the first try because all those things changed and you don't know how to change the parameters of your swing. But you might, if you decided this was your life's work, because you were going to learn how to be good at this, you could sort of feel the pen and sort of wiggle it around and explore it with your eyes closed to say, oh yeah, it's kind of heavy, seems to be a longer pen with a big moment of inertia and sort of slippery. You could feel all those things, get a sense of the pen's properties, and then decide, okay, I'm going to go like this. That is something you do normally when you pick things up. You don't know exactly what they're going to be like before you pick them up. Pick up a hammer, you don't know how heavy it's going to be, but you can feel it. So can we do the same for our robot? So here's the robot just doing its thing once, and a human just hand-coded a trajectory for it. The trajectory consists of two things. One is the movement of the arm. The other is the fingers release slightly so that the pen can move, and then they grip to stop it at the end. So that's the trajectory is this motion and the opening and the closing. So the problem, as I say, is you've got these different mechanical properties like the mass, the friction, center of mass. And well, here's our GelSight sensor we're going to use. And this one's a nice shape. It's pretty compact. We call this the wedge sensor. And as you can see, it's giving you all kinds of nice data. And if you put a pen on it, you can track the pen's motions, and you can also capture the pose of the pen by fitting an ellipsoid to it. So you get a compact description of it. So we're getting all kinds of nice data to use in our task of trying to swing up this pen. And we're going to do it using what is called in the haptics business exploratory procedures. So what kind of wiggling and shaking and twisting is going to work for us to discover the properties? Well, what we ended up with is one is tilting it. You just tilt it at some angle. You can feel the torque and the weight. And you can shake it, which gives you other information about those things, plus information about friction. Now, I want to be clear. We're not telling the robot anything about mass, moment of inertia, or friction. We don't even know about those things. It's going to have to figure it out by itself, and of course, it's not going to literally figure those things out, because what does it know about physics? But it is going to figure out that certain things it discovers while manipulating it in this exploratory procedure, it's going to learn that certain things correlate with what happens when it attempts to do this swing up. So it does this exploratory procedure, it does the swing up, it sees what happens, and it does that a lot. And so here's the templates. That is, these are basically the models of the pens. And So you can adjust them. You can make them all different masses. You can move things around so the moment of inertia changes, center of mass changes, change things around at the tip so the friction changes. And just to show you that these are important, here's some examples of attempts. So the robot's going to do the same thing for both of these. You can see they're built slightly differently because that mass was moved a little bit, and you can see it makes a big difference. The robot gets a completely different result depending on that rather small change. Or if we change the friction of the place where it's gripping, same story. It gets very different results when we change the friction. So knowing about these parameters is critical to success. And of course, in the modern era, it's all machine learning. Once you've got everything set up, then you do machine learning. And that means data, lots of it. And that means, well, it could be there's some person's going to stand there and keep handing this template to the robot over and over again, 24 hours. Or it could be you build a second robot to feed the thing to your first robot. So that's what we have. There's our robot with its gripper, with the object, and this recycling system, which is another baby kind of robot that's going to catch the object and hand it back like this. So the robot arm does these exploratory procedures, watches what happens, then hands it back to the recycling robot and picks it up again, and does that all night. But let's see what information is it picking up. This tilting operation, basically, because of gravity, it gives you kind of a torque, as you get this twisting of the skin, as shown by the arrows, and that's going to depend on the mass and center of mass. Again, of course, the robot doesn't know anything about torque, any of these concepts, torque, mass, any of that. It's just got the raw data. And then it's also got the raw data from the shaking, which is a bunch of little arrows showing how it's moving. So you take all this data, and since I don't really understand neural nets, everybody in my lab does, but I don't. So I'll just say you run it into a neural net. All right, so you do that, you take that stuff, it's got its own little neural net. You combine those, and this is going to give you a low-dimensional description that captures the properties of those objects. And then you also have all the data about what the robot did, these attempts at flipping the thing up, and you find out how successful it was for every different time it tried. Basically, what it's suggesting is the timing of exactly when it lets go and when it regrasps. So you put that all together, and ta-da, you get a result. And here's one result. Here's 4 objects that it hasn't seen, or it doesn't know what they are. And we hand them to it. They're all different. It has to do its exploratory operations before it does the swing up, but then it does the swing up, and voila, it's successful. It gets them all standing up. pretty well. And what's really interesting is if you look inside the neural nets, if you look at how the data is being distributed, it looks like these different properties that that we would label with these physical names like friction, center of mass, and so on, which the robot doesn't know about, but it is implicitly discovering them, discovering something equivalent to them, as it builds this representation to enable it to do this task. So I think that's exciting. I mean, it's going to be similar to the case with a human being, right? I give you a hammer, I say, okay, play with this so you get a sense of how to swing it. And then I ask you, okay, tell me, what do you think, where do you think the center of mass is? And you'll say, I have no idea. But your mind and your body have figured out what's important, not the physicist's version of what's important in terms of these units of center of mass or whatever, but what your system, what your arm and brain and so on know is important in order for you to do the task. And so that's a direction that robotics clearly has to go, is toward not having explicit physical models that are phrased the way a physicist would phrase them, but are functionally adequate models that capture the physically important parameters. All right, so to summarize on the Swingbot, it's a nice example of how we can use tactile sensing in an exploratory procedure. We can extract information about these physical variables. We don't get the literal physics variables, and we don't tell the robot anything about them either. It just has to figure them out or something equivalent to them on its own so it can do the task. All right, I have a little extra time, so I'm going to skip forward to this. I want to mention this other kind of finger we've been developing. Brandon Ribeiro and Felipe Vega built these rounded fingers for the Allegro hand. The Allegro hand is a fairly dexterous hand that's sort of humanoid. And we're looking forward to doing interesting things with it. But to begin with, we want to have good fingers. And it takes a lot of rethinking of the whole GelSight illumination system to get these. But we've got nice fingers now. And I just want to give you an example of a demo that Brandon did. All right, so there's the robot with its fingers. And Brandon sloppily sticks a jar in there, and now the robot's job is to get the lid off. The robot there's no vision. This is all touch. And so the robot doesn't know exactly where the thing is to begin with. By the way, in the right is what's coming out of the sensors. It's kind of hard to see. So initially, it's sort of in the wrong place. The robot has to wiggle its fingers around to get things positioned correctly. And as it's doing it, it keeps on moving around, right? Because it's not nailed down. It's not glued to the thing. So it has to keep on adjusting its position so it can do this task. And it's just using the tactile data, and finally uses the tactile data to detect when it's loose enough that it can lift it. So it's a nice illustration of the possibilities we're looking forward to going beyond these two-finger grippers and using tactile sensing and multi-finger grippers that are capable of more fancy kinds of things. All right, so to summarize, once we have good tactile sensors, we can do lots of great things. We can estimate object properties. We can provide feedback for reactive control. Throughout, we're gathering geometry information from the fingers, which turns out to be tremendously useful for lots of things. And the most important thing of all, we can make cool demos. So thank you very much.
Awesome. Thanks for the great talk. It was awesome to see kind of the interesting beginning of how you've used multiple interests to create GelSight and now the recent developments. Are there any questions? If no one's speaking, you can just unmute yourselves, and if someone else is speaking, you can put it on the chat and I'll call you up.
Could you explain a little more how the metal flakes and the gel are physically intermixed and what the camera is actually looking for?
Okay, so you start with this chunk of clear gel, which is just, you know, a piece of soft rubber. And now you want to make some rubber paint. Rubber being the what they call the binder, and the flakes are the pigment. And the flakes are directional, and when you lay them down, they land semi-randomly. So it's kind of like, it ends up sort of like the frosted side of aluminum foil. But that's all it is. It's a thin layer of rubber with the flakes lying in it. They're at a slightly random angle, so they spread the light. Many times we actually don't use the metal flakes. We use just gray pigment, just matte or Lambertian gray pigment. And in that case, we've just got a layer of gray paint. It's rubber paint, gray paint on top of the gel. And we have the lights coming in at a grazing angle, so they're making a nice shaded image. That's actually the more typical thing we do. But the interaction between there's nothing fancy. It's just that the skin, when it presses against something, it changes its shape, and you can see the shape, just like you can see the shape of any surface by the way the light reflects off of it.
Adrian?
Instead of cars, when do you get to people in terms of surgical robots doing this?
Oh,
Because right now, a lot of what goes on is camera limited in both in terms of invasiveness and capability.
right. That would be terrific to allow surgeons to have the feelings that they would like to have, because classically surgeons can feel inside, they can feel.
Did I say anything about surgeons? I'm a doctor, by the way, so I can do that.
What did you say?
I say, did I mention surgeons being in the loop?
Oh, I see. You don't want the surgeons in the loop.
No,
Oh,
I'm
you're
not a
great.
surgeon. I'm an engineer, doctor.
Okay. When are we going to have surgeons out of the loop? Well, let's start with surgeons in the loop. Because we have surgeons in the loop now, right? Doing robot-assisted surgery. And the robots they're great because they allow you to work at very small scales with great precision. But they're not great because they don't give you tactile feedback. Well, for that, we need good tactile sensors that are really small. And we need good haptic displays that can relay that information to the fingers of the surgeon. We don't have either of those, but maybe eventually we will. And of course, if you eliminate the surgeon, have the robot do it all, still you need to have the little, you have to have the small fingers that can get in there and actually feel those things. That would be great, and maybe someday we'll get there.
Eric?
Sorry, I was muted. So because GelSight is it's not resistive or capacitive, you basically have an optical output, which is very convenient for sticking into a neural network because that's what they've been optimized for a long time. So can you combine this with additional optical input, like a externally mounted camera that's watching the jar lid being screwed on, and produce even better results?
Oh yeah, definitely. We have, and other people have, and we will continue to do that. I've told you about stuff here that's completely tactile driven, because we're trying to challenge ourselves to do everything we can just with that signal. But clearly the right thing to do is to bring in the visual signal as well. And I have to say, this is a point that Russ Tidrake first impressed upon me, is the importance of the fact that geometry is like really just this natural basis for everything in robotics, because the robot is in the world in some configuration, the world has some configuration, and it's easy to use vision to extract this geometry. And now with GelSight, at the fine scale where you're touching, you get geometry there too. So you can fuse that information from the tactile information and the visual information, and you can fuse it in this common language of basically point clouds telling you where stuff is. And yes, that's definitely the direction to go.
Thanks.
Mahdiar, hopefully, sorry if I pronounced it wrong.
Yeah, it was good. First of all, thank you for the talk. My question is with regard to the Swingbot. So the object you were manipulating was a rigid object, meaning whatever happens within the gripper is directly translated to the tip of the object. So I wonder if you've tried doing something similar with more flexible objects, like sort of the cables you showed, like maybe having the robot swing the cable and try to hit an object, for example. And do you think if that would work?
Yeah, that's a really interesting idea. So I guess in the cable work, we made a step in that direction, because the control system, which is based on training data, it learns something about what the effect is going to be, how the pose is going to change of this cable, how it's going to change when you make a movement. So it implicitly has some physical information about the cable and its weight and flexibility in there. But it's a very interesting idea to try to capture more complex information. We haven't done it, and I'm not sure we have anything planned to do that, but we do want to continue working with flexible objects. We're doing some work. This is more work with Alberto Rodriguez's group. We're working on fabrics, where we think the tactile sensing will be helpful. And I think that probably we will have to start building models of the fabric behavior that include things like its stiffness, its weight. And again, there's a question whether we'll explicitly build those or everything will just be learned. But yeah, I think that's a really interesting direction to go.
Thank you.
Terry?
Oh, hello. Hi, I just wondered if you had tried to find like the optimal value of what the GelSight sensor stiffness will be, or, I mean, the silicon layer, or, I mean, do you think there's like a single optimal value, or whether the future of hardware is, whether it's able to, change stiffness on the fly?
Oh, changing thickness on the fly is a cool idea. I don't know. So there's a bunch of parameters. In addition, of course, there's the size, the overall size of the things, and we're doing them sort of thumb size right now. There's the thickness of the gel part. There's the thickness of the skin. There's the hardness of the gel part. There's the hardness of the skin. All of those are sort of up for grabs. We have our stuff is kind of comparable to a human finger in terms of the thickness and hardness and softness. But certainly for their applications where you want to go, where you want to change those things, you want to change the size, of course. If you're trying to work with very light touch things, or you're trying to detect very subtle variations in texture or something, you want a very soft gel and a very thin membrane on top of it. When we talk to people in industry, they say the most important thing for them is durability, because they want their machines to run 24 hours a day, day after day after day, without changing anything. So in that case, you're going to have a harder gel and a thicker membrane, and you'll give up some of the sensitivity. So I don't think there's going to be a single best answer. I think there's going to be a range that'll depend on the application.
Salah?
Yes, thank you. I was interested in the Swingbot. We're doing very relevant similar experiments on humans on how they use preparatory movements to manipulate an object. I was just wondering if you know off the top of your head, like approximately how many exploratory trials did the Swingbot need per new object it faced?
Well, I don't know if you could say that for a single new object. I mean, it trained on the ensemble of all of these at the same time. Then you introduce a new object, which is not exactly the same as any of the other objects, and it just goes immediately, because it already has experience with all these other ones that are sort of have surrounding properties. So it doesn't have to do multiple experiments when you give it a new object, because that object is it sits in the same space that it's already trained in. Now, if you went outside that space, you might be in trouble in that case.
Thank you.
Adrian?
Sorry to unmute. What is, I know you half answered this question, but what is the physical limitation to the GelSight approach in terms of miniaturization? So where do the limits sit in terms mechanically, I guess is what I'm saying, where you stand now?
All right, so let me tell you about a couple of mechanical limits. So one question is that, which interested us early on, is how much resolution can we get out of this thing? That is, because you can get very high resolution signals out of it. And indeed, what ended up happening is my postdoc, Kimo Johnson, who did the early work, founded a company called GelSight Inc., where they do they measure surface microgeometry. They measure, it's called profilometry, and you can make micron scale measurements. So resolution of a couple microns in X and Y, and a tenth of a micron in Z. So if we really worked at it, probably we could get better than that. But it's on that order of magnitude in terms of what resolution you can possibly pick up. In terms of squeezing down the size of the device, well, I don't know. That's going to take, we're just going to have to try. We're just going to have to keep squeezing and squeezing. You know, in principle, if you use fence, there are these endoscope cameras that are really teeny tiny. The gel will have to have some thickness, and the membrane will have to have some thickness. So I don't know where it will end, but it potentially could be quite small.
Just a quick follow-up question. Is there a multiple of the camera size that you could mention? In other words, we know that these endoscope cameras are now 0.6 millimeters to a millimeter on a side. Is there a multiplier that you would apply to that?
Well, let's see. So the camera has to be at some distance from the surface that it's looking at. But we can, you know, do some optical tricks to keep that low. So I would think if your camera's on the order of a millimeter, you could make a sensor that's, you know, a couple of millimeters on a side. I mean, in principle, we have to get the light in there. It's also a question of the accuracy, because you can make using this method, you can make a crummy sensor pretty easily and without thinking much about the optical design, because you'll get some, almost no matter what you do, you'll get some interesting data out of it. But if you want to get good data that really takes advantage of the information, then you need to be careful with your optics. But you might not care about getting all of the data out, in which case you could go with a kind of a sloppy design and make something really small.
Tariq?
Hello. Yeah, thanks for the great talk. So I was wondering about the simulation of GelSight. So like, as you know, like the learning-based methods like deep learning or RL requires a lot of data collection. And in the Swingbot work of you had this procedure for collecting data, but for every other application, you would have to redesign that procedure, right? So if there was a simulator for the GelSight, that would be, I guess, perfect for learning a variety of tasks with this learning-based method. So is there any interest in your group for building? And if there is, like, what are the limitations of building such simulator?
So that's a great point. And just to emphasize that point, not only did we, so running the Swingbot overnight is one thing, but think about poor Wen-Zhen when she was doing this thing on hardness. She actually had to physically build all these models of different hardness. They're a very tedious way of getting training data. Yeah. So clearly, simulation is the way to go. There are several groups that have done some simulation of GelSight or GelSight-like devices. I think that works still somewhat primitive state. I mean, doing a good optical simulation of real-world optics is not trivial. But the real problem is you have to simulate soft materials, which people aren't very good at. And you have to simulate friction, which people aren't very good at. So the fact is that friction and the deformation of soft materials are active topics of investigation. People are making a lot of progress on them. So hopefully they'll get good. And hopefully this whole thing will get good, and we will be able to do good simulations. Right now it's starting, but I think it's clearly the way we would like to go. More generally, on these questions of how do we design the optics of our device to get it compact and so on. Right now, the way we design things, or to make those rounded fingers, which required some fancy light piping optics, the way we make our fingers is by building them one at a time and trying them out. And that's really tedious. So if we can learn to simulate that, it'll be a great help.
Thank you.
It's a bit past 3 p.m., so let's do the last question. Rashida.
Hi, Professor. Thank you for such a wonderful talk. So we look at how humans prepare objects with unknown internal dynamics. And I was wondering if there's any interest in controlling an object, such as a bell, to like a metronome beat.
I know nothing about that, except that it's fascinating. Clearly, humans can learn to do that sort of thing, or you can pick up a bottle that's half full of water and you can kind of judge how full it is by shaking it. And again, that's the sort of thing we, over our lives, have sort of learned to do intuitively. So it's a fascinating skill, and we haven't worked on it, but I think it's a great thing to work on.
Awesome. So let's leave it here. Thanks a lot, Professor, for coming to the seminar.
Pleasure.